Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying differentiability lecture 1. So it's been a month since we have taken any lecture. So we'll be continuing after the continuity lectures and this is differentiability lecture 1. So let's start. This is QOD 18, just take the screenshot. I've also posted this on the group itself. So what do we mean by derivability, differentiability, differentiation, derivatives, etc. So all of these have more or less similar kind of meaning. So we all have studied that velocity is nothing but instantaneous rate of change of displacement, right? We have studied that in physics in class 11th, right? So what are we doing over here? We are just calculating the rate, and that rate is instantaneous. Like it's just at one point. It's not average. It's at just one point. So let's say this is the trajectory of the path. So we are calculating the rate over here. What kind of speed or what kind of velocity the person is having over here. So that is the practical application of differentiability, right? So what is the geometrical significance of differentiability or derivatives? So let's say we have a curve over here and we want to find out slope of this curve at this particular point. So for that, we'll be using derivative. So basically derivative will give us slope at this particular point. So this is the basic definition. These are the basic concepts which you already know, right? Now let's talk about right hand, left hand derivatives. And before that, what we do, we'll see how these left hand and right hand derivatives are being derived. So basically, how do we get to derive the formula of derivatives? So that is a very standard approach. Let's say this is our curve. Now here what we will be doing, this is point A and this is point B. So let's mark the coordinates. So let's say this is A comma f of A. Let's say this function is fx. So this is fx. So this point will be f of A and let's say this point is B comma f of B, right? Now, why am I doing this? Why I'm drawing this secant for this particular curve? Because we want to find the limiting case of this secant that will become tangent. So basically, if we shift this point B towards left, so if I keep on shifting towards left, then there will be one point that this secant will become tangent, right? So A and B are very close, like very close. The distance between A and B is infinitesimally small, right? In that case, that limiting case, that will give us secant to tangent, that will convert secant to tangent, that particular limiting case, right? So we kind of know that we have to use limits over here. So let's talk about this case. So what we'll do, we'll find out the slope of the secant. So that will give us, slope would be delta y by delta x. We all know that, right? So what is delta y over here? That is f of b minus f of a divided by b minus a. Now let's consider a limiting case. So we know that b is nothing but a plus h. We all know what is h. H is very small number, very small positive number. So we have taken b so close to a that b equals to a plus h. So basically this will give me f of a plus h minus f of a divided by b minus a would give me h. Now you can see that how the derivatives formula came. Now we will call this as right hand derivative. Why right hand derivative? Because we are approaching from right. We are not approaching from left. We are approaching from right. We are reducing the distance from the right side. So that's why this is called f dash a plus. A plus means towards the right side of a or right hand derivative. Similarly, you can find out that f dash a minus would be f of a minus h minus f of a divided by minus h. Exactly similar kind of derivation, just you have to approach from the left side. So these are the two final formulas, f dash a plus or right hand derivative equals to limit h approaches 0, f of a plus h minus f of a divided by h. Right hand derivative, okay, no, this is not right hand derivative, this is left hand derivative. Left hand derivative would be f dash a minus equals to limit h approaches 0, f of a minus h minus fa divided by minus h. You got to understand the formula. You got to understand the derivation from where these formulas came. Now let's talk about existence of derivative. How do we know that the derivative is existing? So the first condition is right hand derivative LHD, RHD should be equals to LHD equals to some finite value. Just like limit case, right? In case of limit, what do we say? Left hand limit equals to right hand limit, and that should also be a finite value. Similarly, over here, right hand derivative equals to left hand derivative equals to some finite value. So let's say if this is the kind of case we are talking about, and we are talking about this point, you know that slope is existing, but that is equals to infinity. We cannot define infinity, right? So that's why in that case also we say that derivative is not existing. Now, geometrically, what do we mean by existence of derivative? For that, we have to think in terms of slope, right? So when we say that derivative is existing for a particular curve, we mean to say that geometrically, unique slope is existing for that particular slope at a particular point. For example, let's say we have this function over here. Now you can say that this right hand derivative is, let's say, 1, and this is also 1. We can see that these are two parallel lines. So we can clearly see that the derivative value is same, right? But this is not giving us a unique tangent. So at this point, you will get this tangent, and this point you will get this tangent, right? So there are two tangents. So we have to find exactly one tangent at a particular point. Then only we can say that geometrically that the derivative of that function at a particular point is existing, right? So RSD equals to LSD equals to finite, and also the tangent should be unique. In this case, you can clearly say that RSD equals to LSD equals to finite, so derivative might be existing, but over here tangent is not unique. So these are the total conditions for the existence of derivative. Now let's look at this illustration. Find the derivative of fx equals to mod ln x at x equals to 1 using all approaches. So the first one is first principle. First principle is nothing but these formulas. Let's calculate f dash a plus. Here a is 1, so we will be calculating f dash 1 plus. That would give me limit h approaches 0. F of 1 plus h would be mod of ln 1 plus h minus ln 1 divided by h. Now we know that this is 0. So what do we get over here? Limit h approaches 0 ln 1 plus h mod divided by h. Now we know that h is a positive quantity, and 1, we know that ln 1 is 0. So anything lesser than 1 would give us ln as negative. Anything greater than 1 in case of ln will give us positive. So this mod will open as positive only. So that would give me ln 1 plus h divided by h. So this is the standard format. That comes out to be 1. So we got to know that f dash 1 plus comes out to be 1. Now let's talk about f dash 1 minus. So f dash 1 minus, sorry, that would be limit h approaches 0 mod of ln 1 minus h minus ln 1 divided by minus h. Now we know that this is 0, and what is this? This should be some negative quantity, right? So that would give me minus of ln 1 minus h divided by minus h. Now this is the standard format. So that is 1, and that would give me minus 1 as the answer. So this is 1, this is the standard format, and additional minus 1 over here. So that would give me minus 1. So f dash minus 1, f dash 1 minus is equals to minus 1, and f dash 1 plus was 1. So we can see that these two are not equal. So that is why derivative does not exist at x equals to 1. Now what would be the second approach? So we have been given fx equals to mod ln x. Right. Now what do? We'll open the mod and put the conditions. So fx would be ln x and minus ln x, right? And this would be case for x greater than equals to 1, and this would be x less than equals to 1 greater than 0, right? This would be the case. Now what do? We directly differentiate it. So what we'll get 1 upon x for x greater than equals to 1, and we'll get minus 1 by x for x less than 1 greater than 0. Now the critical point to check is 1, because we have been asked it 1, right? So if we put 1 over here, so this will give me 1 plus, because this is on the right side of 1 and this range is on the left side of 1. So this would give me f dash 1, 1 plus, and this would give me f dash 1 minus. Sorry. So when you plug in 1 over here, you'll get minus 1. And when you plug in 1 over here, you'll get 1. So we can see that these two are not equal. Now the third method would not give us the values, but it will tell us that if ln sorry, if ln(x) is if mod ln(x) is derivable or not at x equals to 1. So let's check that out. That is the graphical approach. We know that graph of ln(x) looks like this. So this is the point x equals to 1. This is ln(x), fx equals to ln(x). Now, but we have been asked over here mod ln(x). Now we know that mod ln(x) would never be negative, right? So what we do over here, we'll take the mirror image of this graph about the x-axis. This is how we do the mod, right? For any function, let's say we have a function like this. So this is our y equals to x function. And when we say, when we talk about mod x, what we do, we just take the mirror image of this one. So this angle equals to this angle and similar kind of slope, but on the negative side, right? So this is how we take the mod for the graphs in the graphical method. So what we have done over here, we have just taken the mirror image of the function, part of the function which is lesser than 1. So that comes out to be like this one. Now we know that when we have a sharp corner over here, we can clearly see that just on the right side, derivative is positive. Just on the left side, derivative is basically slope is positive over here and slope is negative over here. So we can say that the sharp edges or corners, we can clearly say that derivatives are not equal. So that's why derivative doesn't exist over here. Now, since we have seen few examples, let's look at the theory for the reasons of non-derivability. The first one is discontinuity. Now, in the beginning, I gave one example. Let's say this is a function and this is a closed circle over here, open circle over here, and this. So it's given that these two slopes are equal. So we can clearly say that, let's say this point is A. So f of A plus, f dash A plus equals to f dash A minus. But still, this function is not derivable this at this point, right? Why? Because we cannot draw a unique tangent over here. We'll get two tangents, one here, one over here, and one over here. But that is the geometrical meaning, right? That is the geometrical inference. How do we define it mathematically? For that, we introduce the concept of discontinuity. So if the function is discontinuous, we'll always get two tangents and we won't be getting a unique tangent, right? So that is why if the function is discontinuous at a particular point, that means non-derivable. So that makes the first point clear. Now, as we discussed recently about the mod ln(x) graph, sharp turning points. So what is happening over here? Let's say we have a graph like this. So we know that, let's say this point is A, just in the vicinity of, right vicinity of A, that is A plus, and in the left vicinity of A, that is A minus. You can clearly see that this f dash A plus, that would be some positive value, and this f dash A minus, that would be some negative value. So both of these terms are not actually equal, and that can happen at any sharp edge. So if the function is smooth, let's say function is smooth actually like this, so we can clearly say that just in the vicinity, both the slopes are tending to be the same. Limiting values are same, but not in this case because we have sharp edges over here. Let's say we have a graph like this. Over here, one slope is like this and one slope is like this. We can never say that these two, even in the limiting case, these two are equal. In this case, in the smooth edges, limiting values are same. Right? So that defines our second point. Now let's talk about the vertical slope. Now in the definition itself, I talked about this kind of graph. So let's say we are talking about this point. This point is A. So we know that over here slope is actually infinite. This is the vertical line. Slope is actually infinite. And when we defined differentiability, what do we say? LHD equals to RHD equals to some finite value. Why? Because we are talking about the limits over here. And when we find out the limit, actually when limit is infinite, we cannot really define it. So limit has to be some finite value. And so is the case for slope. Slope has to be some finite value. And that's why in case of vertical slope, we say that the function is not derivable. Now we know that when we have the function as sin x, then the first derivative is equals to cos x. In case of fx equals to ln x, the first derivative is 1 by x. But how do we get to derive these functions, right? So let's look at those examples with the help of first principle. So we have fx equals to sin x over here, and we have to calculate f dash x. Let's say we are calculating f dash x plus. What that would give me, h approaches 0, sine of x plus h minus sin x divided by h, right? Now we know the formula sin c minus sin d, right? So what that would give me, 2 cos of c plus d by 2, that would give me 2x plus h by 2 dot sine of c minus d by 2, c minus d by 2, that would give me sine of x by 2 divided by h. Now you can put that h over that 2 over here. Now this becomes the standard format. So not, this is not x, this is h. So this becomes the standard format, that is equals to 1. Now what we are left with, cos of x plus h by 2. Now we know that when we have the limiting case, limit h approaches 0, in that case this is nothing but cos x. So this is how we get the derivative of sin x as cos x. Now let's look at the case of ln x. So we have fx equals to ln x, and we want to find out f dash x plus. That would give me limit h approaches 0, ln of x plus h minus ln x divided by h. Now I'll do few adjustments over here. What I'll do is I'll write ln of x multiplied by 1 plus h by x minus ln x divided by s. Now just one piece of advice, don't use L'Hopital over here to derive it, because in case of L'Hopital we are using derivatives. So we cannot use derivatives to derive derivatives, right? So that would be the contradiction. So in that case, we'll be using the standard or regular methods. So what I've done is over here, I've taken x out, and that becomes x multiplied by 1 plus h by x, right? Now we can use the log property. That would give me ln x plus ln of 1 plus h by x minus ln x. Now this gets cancelled out, divide by h. Now what I'll do over here, I'll multiply and divide by x. So this again becomes the standard format. Ln of 1 plus anything which goes to 0, divide by the same thing, that becomes 1. So that would give me 1 by x, right? So this is how we derive the derivative of ln x with the help of first principle. Now you all must be remembering that we talked about open and closed intervals in case of continuity. So exactly similar is the case for derivability. So let's take the case of open interval first. So we have, let's say a comma b, or let's take the values. Let's say we have 1 comma 4, and we have to talk about the differentiability of function fx in this range. So except 1 and 4, except the points 1 and 4, we have to check it all points, all the critical points at which function fx might be not differentiable, non-differentiable, right? So we have to check it all the points between this range except the endpoints. This is the case for open interval. Now let's talk about closed interval. In that case, what we'll be doing, we'll be checking, we'll be doing this case, we'll be doing the open case as well, but also we'll be checking at the endpoints. For 4, we'll be talking about only left-hand derivative. Why? Because let's say this is the number line and this is 4 point over here. We know that we are not talking about these values. We are not talking about these values. We're just talking about these values. So what this to be derivable, we have to check it the left hand side. So we'll be talking about left hand derivative over here, and we'll be talking about right hand derivative over here. So along with the open interval case, we have to check at the endpoints for right hand derivative and left hand derivative. That would give us all the points in which the function is derivable in this closed interval. Now let's try to understand all these concepts with the help of one example. So we have been given a function fx equals to modulus of 1 minus 4x square and gif of x square minus 2x, and these are the ranges. So let's try to focus on this function as of now. Let's try to plot it. So as of now, I'm not plotting the modulus. We just convert the graph after plotting the inner part. So at x equals to 0, this function is going to give me 1. And at x equals to 1, we'll be getting minus 3. So this is 1, and we'll be getting minus 3 over here. Now we know that this is a quadratic function, and also the coefficient of x square is negative. So we'll be getting a parabola that is facing downwards, something of this sort, right? Now we have to convert this graph into the modulus one. Now, as we took one example earlier, what we do, we just take the mirror image. So we'll be getting something of this sort, right? Just something of this sort, right? So the function comes out to be like this one. So what this point would be, that would be 1 by 2. If we put 1 by 2 over here, we'll get 0. So that point would be 1 by 2. So we got to know the function of the first graph in this range. Now let's talk about the second graph. So we have x square minus 2x over here. At x equals to 1, we are getting x equals to, at x equals to 1, we are getting minus 1. And at x equals to 2, we are getting 0. Now this is also a quadratic function with coefficient of x square as positive. So what we'll get over here, we'll get a parabola upward facing. So this would be the kind of, this would be the kind of trajectory we'll be getting over here with a closed circle over here, right? Now we know that anything in this range, when we take any value between 1 to open 2, not including 2, 1 to open 2, we are talking about this range as of now. When we are talking about this range, we are getting this as minus 1 only, because this is 0 and this is minus 1. So anything in between this, and we take the GIF of that function, that value, that will give me minus 1 only. So the actual function would be open circle over here and close circle over here. So at 1, it's minus 1. At any other value in this range, it's also minus 1 because of the GI function. And at x equals to 2, that is 1, this is 2, that would be exact 0, right? So this is how our function going to look like. So this is 1 point, and this is open circle over here, this is 2, right? So this is how a function is going to look like. Now we have to find the points of differentiability or non-differentiability. So the first major point comes out to be this one. Because of the sharp edges, that would be x equals to 1 by 2. At this point, this function is non-differentiable. And let's talk about the this value. Let's talk about this value, x equals to 1, because over here, this value is over here and this value is over here. So on the right side, it's minus 1. On the left side, it's something else. So we can clearly say that x equals to 1 is also a point where the function is not differentiable. Now let's talk about the point 2, x equals to 2. Now we know that when we are talking about closed intervals, we have to look at the endpoints as well, right? So this is the endpoint, and if we are talking about x equals to 2, we can clearly say that in the left vicinity, the value is minus 1. So basically, it's not continuous over here. At x equals to 2, value is 0. At the left vicinity, it's not equals to 0. It's actually minus 1. So if the function is not continuous, then it's also not derivable. So we have got 3 points over here, right? So this example covered all the concepts of open interval and closed interval. So today's lecture was till here only, and we covered few basic concepts and examples. And in the next lecture, we'll be talking about few more advanced concepts, and probably we'll be covering the entire differentiability chapter in 2 or 3 more lectures, right? So let's meet tomorrow for the next lecture. Thanks for watching.